A group of scientists just detected a massive structure inside Earth's core that changes everything. But for how long has this secret been buried? How was it blown? And what's the implication of the discovery? Keep watching as we give you the full insight on what this discovery means for us as humans. After analyzing earthquake data, a group of scientists from the Australian National University believe they have found evidence of the Earth's inner core hiding another more inner core within it. The layer, which looks like a solid metallic ball, is previously unknown, and the best name they could give it, at least at the moment, is the innermost inner core, IMIC. Now, you may not remember, but there was a hypothesis about the existence of a mysterious internal metal ball residing within the inner core about 20 years ago. However, it has never been seen in detail. But now, with this recent discovery, as published in Nature Communications, is the first time scientists would have concrete evidence to support the hypothesis. If we are to follow what we have in most textbooks, the Earth was believed to be about 7,900 miles or 12,750 kilometers in diameter. Its internal structure is made up of 4 components, namely a rocky crust, a rocky mantle, a molten outer core, and a solid inner core. Earth's inner core is a solid metal ball that is about 75% the size of the Moon. It is believed to spin at different speeds and directions when compared to our planet. It can do that because it's located within a liquid outer core. However, scientists don't know how fast it spins or whether its speed remains constant over time. It was only in the 1930s that Inge Lehmann, a pioneering Danish seismologist, discovered that Earth had a metallic inner core, which is about 1,500 miles, 2,440 kilometers in diameter. It had been thought that Earth's core was a single molten sphere with an inner core separated from the planet's surface by thousands of miles of rock, which makes it very difficult to study. So how can we use conventional probes to explore deep inside the Earth, where the temperatures are too hot and pressures too extreme? The inner core's temperature, which is estimated to be about 5,500 to 6,000 degrees Celsius, or 9,930 to 10,830 Fahrenheit, similar to the Sun's surface temperature. Therefore, the only way scientists could have an idea of what's happening there is by relying on seismic waves. Though these waves are known to be destructive, they serve as powerful tools of discovery in the hands of geologists. The group of scientists that discovered the potential 5th layer of Earth have been committed to understanding Earth's origin and evolution and how it became habitable to life. Therefore, they conducted an intensive study of Earth's deep interior, analyzing the behavior of seismic waves from large earthquakes in the last decade, only to make this shocking discovery. In 2002, some researchers suggested that the inner core might be hiding another layer inside of it. Scientists at that time relied on observations of the seismic waves that plunged it deep into the Earth. Unfortunately, they only had sparse data available to them. What they needed was sensors placed on the opposite side of the planet from the earthquake so as to collect a seismic wave carrying data from the Earth's core. However, such locations where they needed to place the sensors are often in the middle of the ocean. In recent years, though, more seismic sensors have been installed, allowing scientists to observe the reflections of waves bouncing from the other side of the Earth and rebounding back toward the epicenter of earthquakes. In addition, scientists were also able to detect even the weak signals of these rebounding waves during earthquakes. When an earthquake strikes, it first releases primary waves traveling through the planet from all directions. Then secondary waves or S waves follow. However, only primary waves were detected on one side of the planet for large earthquakes. It only makes sense to conclude that liquids lack the rigidity to allow S waves to glide through. About 30 years ago, Xiaodong Song and Paul Richards, who were both seismologists then at Columbia University, thought of using the waves in the islands to get the clues about the inner core, which was suspended in liquid and doesn't rotate in sync with the remaining planet. Thus, they combed through archival seismic records in search of subtle variations in the travel times of P waves for dozens of earthquakes in the islands over the course of decades. They discovered that Earth's inner core had stopped spinning and may be reversing the direction of its rotation. They believed that iron atoms in the two regions are packed slightly differently. Contrary to her early postulation about the crystal alignment being north-south, Song's investigation reveals that the alignment in the innermost inner core is nearly east-west. During the investigation, they also realized that the travel times of seismic waves through the outer core and mantle remained constant as expected, but P waves going through the inner core sped up a bit with each passing year. The scientists believe that the crystallized structure within the inner core's innermost region is likely different from that of the outer layer. This further explains why the waves penetrate the inner core at different speeds depending on their angle of entry. To explain this puzzling trend, they came up with a hypothesis. They posited that the inner core was rotating faster than the remaining planet by about 1 degree per year. The speed was then gradually realigning the paths of the seismic wave with a north-south axis in the inner core to increase the speeds of the P wave. They also mentioned that the inner core makes an extra revolution inside Earth every 400 years. Then, some years later, another seismologist, John Vidal, now at the University of Southern California, adopted a slightly different method, eventually validating the hypothesis of Song and Richards. Vidal was a specialist in using records obtained from the Large Aperture Seismic Array LASA, an Air Force facility in Montana, which closed in 1978 and operated over 500 sensors in deep boreholes to detect atomic bomb tests. Vidal believes that these seismic waves from nuclear tests remain the best data due to the fact that the source has a precise location. He then used the waves from 2 Soviet underground bomb tests that detonated in 1971 and 1974 beneath Novaya Zemlya, a remote Arctic archipelago. Rather than seek waves that passed through the inner core as Song and Richards did, Vidal chose waves that rebounded off it and registered its spin like the beam of a radar gun. That is, while one side of the inner core was getting closer, the other side was getting further away. Vidal then discovered that the inner core rotated at much more speed than Song's first estimate. According to him, it rotated 0.15 degrees per year faster than the rest of the planet. Interestingly, subsequent work by Song in 2005, after using 18 pairs of South Sandwich earthquakes reoccurring in the same spot over some decades, aligned with Vidal's reduced estimate. Many geophysicists were shocked by the discovery of the inner core's superrotation. They assumed it spun at the same speed as the mantle. They then realized that the rotation could provide clues about how the inner and outer core influences the magnetic dynamo. Some even thought it could help explain the puzzle of why Earth's magnetic poles wander from time to time. And then back in 2021, a team of researchers spotted changes to the structure of iron within the inner core, which suggests a new boundary line stretching about 650 kilometers from the center of the Earth. The researchers also used travel time data for seismic waves traveling inside the Earth as captured by the International Seismological Center. They then used their new algorithm to search through the data to discover evidence of changes in the structure of the innermost part of the Earth's inner core. Although they couldn't find the changes in the iron structure, they demonstrated 2 distinct cooling events in Earth's history. In the most recent times, observational seismologist Than Son Pham of the Australian National University, ANU in Canberra, and another professor with ANU's Research School of Earth Sciences, RSES, led research to provide new insights on the evolution of our planet. Thus, they relied on seismic wave data obtained from some earthquakes in the past decade. The discovery by Pham and his partner provided a line of evidence to substantiate the earlier postulation of the innermost inner core discovered in 2002. Until recently, our knowledge of the Earth's inner core has been through a combination of volcanic eruptions and seismic waves, which are indirect observations. According to Dr. Pham, the Earth's inner core, IC, accounts for about 1% of the Earth's volume and exists as a single body. The inner core is formed and continues to experience a tree-like growth due to the solidification of molten materials at the inner core boundary as Earth gradually cools. This process has been repeated since Earth's inner core was born about 4.5 billion years ago. The latent heat released during the process of the inner core solidification drives the convection in the liquid outer core to generate Earth's geomagnetic field, which protects us and other life from harmful cosmic rays. In a paper that appeared in Nature Communications, the team reports findings that helped to revise geological models of Earth to include 5 distinct layers instead of the conventional 4. As indicated in the paper, seismic stations across the globe recorded the triggered waveforms, which traveled directly through the center of the Earth to the opposite side of the globe, known as the antipode, before returning to the source of the earthquake. According to the team, the findings are critical to explaining how waves speed up or slow down based on their angle of entry as they penetrate the innermost inner core. To ascertain the change, they developed a technique to boost the signals recorded by densely populated seismograph networks. They utilized a method that tracks the echoes from earthquakes. To achieve a relatively accurate result, the team repeatedly collected signals from 200 earthquakes with magnitude 6 and above bounding around the globe. However, the echoing waves are small because they lose energy as they pass through the planet. But interestingly, the team was able to add up the repeated faint signals as they rippled through and around the interior of the planet. They found out that the seismic waves that travel in the about 1,300 kilometer or 808 mile diameter of the innermost core bounce back and forth up to 5 times along the diameter of the Earth, as against a single antipodal bounce documented in previous studies. The travel times of these waves suggest the presence of a distinct internal shell, distinct from the inner core's outer layer, a solid ball of iron to be about 800 miles or 1,350 kilometers wide and 400 miles in diameter. The hidden layer of Earth sits 100 miles below the surface and covers at least 44% of the planet. But some seismologists, such as Dan Frost at the University of South Carolina, did not believe that the discovery of a change in the way that waves travel suggests the existence of a distinct innermost inner core. Frost, who did not contribute to the study, reveals that the results could be more of a gradual change occurring within the core rather than an abrupt and distinct transition. He further thought it was an unnecessary splitting into multiple layers. One of the earthquakes the scientists studied originated in the South Sandwich Islands in Alaska. The islands have subduction of the South American tectonic plate nearby, thus making them earthquake factories. There, seismic waves triggered by the quake bounced off in a location in the South Atlantic Ocean before traveling back to Alaska. The team studied the 2 layers of Earth's inner core, both of which are composed of an iron-nickel alloy. The aim was to investigate the evolution of the inner core. The result would later reveal a greater difference in the impact of the angle of the waves on the speed in the very center of the inner core, a phenomenon known as anisotropy. Anisotropy measurements of the inner core of the Earth based on the travel times of the waves revealed the possibility of the core hiding a layered structure in its innermost part. The team discovered that the 2 proposed layers had different crystal structures. They also found the transition between the inner and innermost cores to be gradual. Despite being made of the same materials as the molten outer core, the metal inner core seems to have different properties, as explained by the scientists. They suspected that the new core might have been formed following a major global event at some point during Earth's evolutionary timeline, thus resulting in a significant change in the crystal structure of the Earth's inner core. Because of this observed change, they believe that the study of Earth's deepest part could tell us more about the evolutionary history of our planet Earth. If that's the case, Dr. Pham believes that the distinct layers could act like a planetary time capsule of Earth's evolutionary history and could provide insights into the events that characterized the Earth hundreds of millions to billions of years ago. But other geoscientists have argued that the iron-nickel alloy that constitutes the inner core simply becomes gradually more organized in its crystallization pattern when at greater depths. According to them, this change in the organization affects the movement of earthquakes through the innermost inner core. By this hypothesis, the inner core has been solidifying consistently throughout the Earth's history, thereby rendering the distinction of an innermost inner core somewhat meaningless. Therefore, the crystallization transition happened gradually, leaving no distinct border between the innermost inner core and the remaining part of the inner core. Despite Frost's disagreement with Pham's interpretation of their findings, he lauds the process of using multiple faint echoes of earthquakes to observe the very center of the planet. According to him, what the team did was help to make more earthquakes accessible to us. Yet, despite the discovery, there are still a lot of unanswered questions about how our planet formed together, especially as it concerns the innermost inner core. Notwithstanding, though, insights derived from the discovery could help with studies of other worlds, especially Mars. Mars is considered a barren planet, having lost its magnetic field about 4 billion years ago. This loss exposed the planet to solar winds and dust storms that carried away the atmosphere and oceans. Although exoplanet hunters could use the knowledge in searching for habitable worlds, the fact that an Earth-like core structure is present doesn't guarantee survivability. Let us know your thoughts about this new hypothesis and discovery in the comment section.